So now let's say that we want to build a neural network. For this, we need some building blocks. We looked at different linear layers for now and different nonlinearities. To find it, depending on the combination of these, we can have different architectures. So one thing that we need is the architecture. Then we want to predict some value and be able to update our model parameters. So we need some objective or loss function or cost function or error function. There are multiple names for them. Sometimes they're interchangeable. In some literature, they're not. So we need something to be able to assess how good our prediction is. We take basically our prediction. We get, for instance, in the supervised problems, we get our labels, and we want to see basically how much is the discrepancy between the target and our prediction. So we need some objective, and then when we had that objective, we need some optimization algorithm that takes that objective, and then based off of that, it optimizes the model parameters. So we will next go over these. In a data-driven approach, where we have some data, and we want to learn parameters of the model based off of this training data, we call basically finding the parameters of the model training or model fitting. So what we want to do is to, given these observations, to maximize the probability of observing these, right? So we assume that our data, our training data D, is sampled from some true distribution P data we call it, and then our model is defined as some sort of parametric distribution family, and we want to find the parameters for this. So given our observed data, we want our parametric model P theta to give high probabilities to the members of that training data, or basically our observations. And we can represent that as maximizing the probability of our basically our data. That's going to be the case in any problem that basically is going to be solved with this model. In the supervised case, we also have some input that our data is conditioned on. So basically in the supervised problem that we are discussing for now, we are maximizing this conditional probability of I given X. Go ahead. Someone was asking a question. Go ahead. Maybe they left there. Unmute him. As a question you can ask again. So just click on this. All right, so we said that in the case of supervised problems, we want to maximize the probability of a conditional probability of our data Y given some input X. So we assume that in this basically training process, we assume that our data is independently sampled from a basically distribution P data, and there is these basically data points are independent from each other. So that's a basically cornerstone of this basically type of solution MLE basically approaches. So we can, if they're independently sampled, we can represent them as a multiplication of the basically conditional probabilities of each data point in our observation or training data. So we can write the probability of our training set as the basically multiplication of probabilities of each training data in our training data set. So we said that we call that basically IID because they're independently sampled from some basically true distribution. Now, and we have this training data, and we want to maximize the probability of observing these training data. So that's mathematically speaking what we are trying to do. We have P of D, and it is parameterized. We want to maximize that with respect to theta. We previously said that instead of maximizing a product of probabilities, we really want, for numerical reasons and various other reasons, we want to write it as a sum of logs of these, right? So we can just apply a sum log, and then it is going to be turned into a sum of these log probabilities. And we are also usually interested in minimizing these problems instead of maximizing, so we can just write it as a loss function. So we said that our MLE estimate, point estimate for model parameters is just arg minimum of these basically model parameters for this relation, log of sum of log probabilities of conditional basically distributions. So that's in general the approach that we're going to take. Now let's move to the optimization model that we use. In deep learning models, we usually, in most case scenarios, we want to use some gradient-based model to train this. And this gradient-based model, what it means that it has a function, objective function. It computes the gradient of this, and it uses the gradient of that objective function as a guide in the parameter space to find the optimal, or let's say that to basically find a good solution. So let's say that, for instance, we have some j, which is a function of theta, our model parameters, and let's say that we only have two variables here, two model parameters, theta 1 and theta 2, so that we can show this on a 2D space. Now I select this point, for instance, this point theta in the space, and the gradient, the direction of the gradient of this function j theta at this point theta is going to give me the direction of the largest change in this function, right? So it is directing this way. So it means that if I move this way, I'm going to have the largest change at point theta with respect to some neighboring point. And if we're trying to minimize our function, we just move in the negative direction to this in order to be able to minimize our function j theta. So we're going to move in opposite direction to this green arrow here. So again, we want to minimize. We have some function j, which is function of x. We compute its derivative, and we use its negative basically direction as our guide in the parameter space. So if we have a function, a multivariate function, which has a larger number of parameters, now what happens is that we can use, again, the same idea, but instead of derivation, we just say that it's a gradient that is helping us. So let's say that we have a function f. It gets some n-dimensional input x, and it returns some real value r. And we can represent all partial, basically derivatives of this function with respect to variables x1 through xn using this gradient, which is just a vector. Elements of each are just our partial derivatives. So now in multivariate functions, what guides us to find the parameter in the parameter space, the parameter that we're looking for that minimizes the cost is the gradient of that function f. So now we have a training data set. This training data set, maybe it includes hundreds of thousands of training data. And if we want to directly take this data and we want to compute the loss function and then basically find a gradient, it is going to be a large number, hundreds of thousands. It is basically computationally expensive depending on the size of your data as well. So we represent our loss function using this equation. We're gonna, let's call it L, a basically per data loss, right? So you have a single data, you have a single corresponding target, you give it to this function and it will give you some loss value. We're gonna sum over the loss for every single training data point in our data set, and we're gonna average over all those, and that's gonna give me the loss for the whole training data. So I want to approximate this. And one method to do that is the stochastic gradient descent. In the stochastic gradient descent, we're saying that I don't go and take my data as a whole. I take it, basically, I divide it into separate bins. I call them mini batches, and I go over this data in mini batches, right? So, and I say that this basically loss for that each mini batch is essentially estimating the loss for the total training data. That's the idea behind stochastic gradient descent. We say that we are representing our loss now with only n prime samples, where n prime is just the size of a subset of all the training data that we have. So let's say that your data is in the order of hundreds of thousands, but your mini batch is somewhere between 10 and a few hundreds, right? Usually that's the range between 500 and 10. So you select those number of data points and you again plug them into this function f, and you find essentially this parenthesis should be on the basically on the other side of x. So it means that this loss function is just comparing the prediction f theta of x and the true label y hat. And at the end of the day, you're going to get some loss. Now the gradient of this loss can be just approximated using the gradient for just this small subset of training data in our data. Okay, so now we have this gradient. This gradient is going to be our guide, and we're going to update parameters according to this relation. We're going to say that I'm going to take a step size in the negative direction to this gradient, and I'm going to have basically a step size thing that I call it eta, that is essentially our learning rate. And I'm going to update my theta using that. This learning rate usually is around maybe 10 to the minus 2. That's the norm, 10 to the minus 3. And depending on the stability of your basically optimization, you can basically push that in order to for your model to have a good solution, or you can actually learn that parameter in basically meta learning approaches. You learn parameters of your learning model. So there are multiple ways to select that. All right. So now in neural networks, we need to find basically an objective function, and we need to find the derivative of this objective function with respect to all the parameters that are in our network. This might look very expensive, and it can actually be if you're not moving smart. And to move smart, we're using an approach called backpropagation. So what is backpropagation? Let's go back and think about our basically initial function. We have some x, we pass it through some nonlinear layer, some basically linear transformation, and we will get some intermediate output. That's going to be input for the next layer, and so on and so forth, until I get to value y hat, which is my prediction. Now, if you think about it, we're essentially giving x to our network, and the network is propagating this information forward to the last layer. Now, in order to, now we basically get our prediction. Using this prediction, we compute our loss function. And now, based off of this loss function, we want to find gradients with respect to all these parameters. So what gradient-based backpropagation does is to get this loss function, it propagates it backward through the basically network that we have, and it computes the derivatives of the loss function with respect to model parameters. And it is going to do that using a basic calculus rule called chain rule. So next we will quickly go over chain rule and see how basically that is. All right, so just to refresh your memories on some basic undergrad calculus, let's say that I have two functions, f and g, And both of them are a map from real values to real values. So essentially, I have some variable x, I give it to function g, it returns me some variable y. I plug this new variable to another function f, and it is going to give me some variable z. So now, next thing, what I want to do is to find the derivative of this z with respect to initial input x. And the way to do that using chain rule is just writing that dz over dx is derivative of z with respect to y times derivative of y with respect to x, right? And that's going to give me dz basically over dx. Now, this can be extended to multivariate functions. So let's say that I have two functions f and g. G is a map from some n-dimensional space to m-dimensional space. So both your input and outputs are vectors of different dimensions. And you have a function f. The first one was g, the second one is f, which is mapping from some n-dimensional space to m-dimensional space to some real value. So this is a map from a vector to a real value. And now what I want to do is to compute the derivative of this z with respect to our initial input x. I can write this as in index notation. I can write it as derivative of z with respect to each dimension dxi. And I can write it as a sum over all dimensions of y, dz over dy, and then all dimensions of y dyj over dxi, right? So I'm just basically finding multiple derivatives, partial derivatives of z with respect to y, x, i's, and I'm writing this as a sum over partial derivatives of basically z with respect to y and y with respect to dxi. So I can rewrite this in matrix format in basically vector notation. And basically, I'm taking this, I'm writing this as a Jacobian. It is basically derivative of a vector with respect to vector. I'm writing it here. And then I have this other thing, which is derivative of a basically one-dimensional variable with respect to a vector, which is going to give me gradient, right? So I can write the derivative of z with respect to anything, the gradient of z with respect to the vectors that initiated it, its parent basically variables, as multiplication of a Jacobian and the gradient. And that's the idea that we're going to use in the chain rule. So, and basically in backpropagation. So, before going there, I want to introduce a concept of computational graphs that can be useful for both debugging a code very much, and that can also be useful to basically describe this backpropagation problem. So let's basically look with an example. So we have in a computational graph, we're representing each variable with some node, and we're representing operators as basically a function of two nodes and or multiple nodes and with output a single variable. And that's without loss of generality. So we can generalize that with multiple outputs as well. And then each directed edge is representing a basically operator that applies on x and outputs a variable z, right? So for instance, I have this very simple example here. I want to represent this relation with some computational graph. I say that I have three variables, x and y and z, x and y and z. So x, an operator, which is just a simple product of x and y, is going to give me a variable z. So I'm going to draw two edges, two directed edges from x and y toward z. Now, another example is I want to write the computational graph for this relation. I have how many variables here? 4, right? So first thing is to write these variables. And then the next step is to say that I'm going to start with one of these relations. Let's say it's that W and X. It doesn't depend on anything else. I'm applying a basically matrix multiplication on this, and that's going to give me some intermediate output U1. Then I'm going to apply an operator, basically a sum operator on variable B and variable U1, and that's going to give me a new variable U2. And then I'm going to apply this ReLU function, maximum of 0 and that basically X, on my U2, and that will give me basically variable H, which is our output. And as a last example, we can also show multiple basically relations using the same computational graph. Let's say that I want to represent these two equations, both of which have W in them. So I will start first from basically writing down the variables that I have. I have lambda, W, X, and Y hat. And I say that I apply the basically dot product operator to vectors X and W. It will give me Y hat. And then next, I say that I have my W, and I'm applying element Y square on this elements of W. And then I take that, so that will give me a new variable U1. And next, I'm going to take that, and I'm going to apply a sum over all the elements. And that's going to give me a sum, right? A new variable U2. And then lastly, I take that variable U2, I multiply basically that with lambda, which means that I'm applying my operator, just simple multiplication on these two basically scalars, and that's going to give me a new variable U3. So that's essentially how computational graphs work. Let's have 5 minutes rest, and we will basically continue with computational graph for background here.
I have a question.
Go ahead.
When you do this back propagation and you have this ReLU function, and how do you handle those discontinuities in when you have I'm sorry, when it is not differentiable?
It is differentiable because, I mean, we're just saying that it is 1 and 0, right?
Yeah.
It is one time differentiable. The second time, it is not. So if it's basically larger than 0, greater or equal to 0, you're going to say that.
Well, it is continuous, but it's not.
Yeah, it's not discontinuous, but we are going to say that the gradient is equal to basically 0 when it's less than basically 0, the function x. If x is larger or equal to basically 1, we're going to say that the derivative is 1, and that's enough for us. The second derivative is where the problem begins for ReLU functions.
Okay.
Because that discontinuity, I mean, it's a step, so that's going to give us a hard time.
Okay, and the second question that I had is, we are taking these linear maps in each layer.
Yes.
I mean, what is that? Does that give any advantage? Or for instance, you could argue instead of having more layers, you can have more non-linearities in each layer, right? So how is that a way to do this?
So I assume that you mean that if your function is nonlinear, then more nonlinear functions will help us to map it better. Is that correct?
Yes, instead of having more layers, right?
But it is, so those nonlinear functions might not really, might not represent the type of relation between your inputs and outputs. Sure, if it is exactly that. So if your data is created exactly with the type of nonlinearities that you're trying to use, multiple of them, then fine. But in reality, that's not going to be the case. The relation between X and Y is more complicated than that in many scenarios. So what you need to do is to learn it rather than guessing that, okay, this is gonna be able, we're gonna be able to represent this with multiple nonlinearities.
Okay. Okay, thank you.
Sure, but I mean, in reality, there are lots of research to understanding why neural networks are the way that they are. So it's an open question. It's an open question why neural networks are basically working the way that they are working with this incredible basically performance. So that's
okay.
an open question.
The way I understood it was, okay, because linear algebra is very well understood. That's the tool that's the basic element of each layer. So is a linear transformation, so that makes it easy to build off of prior knowledge. But that's a question that I'll be interested to know more about, as to why not having each layer as linear, but getting nonlinearity over multiple layers is better than having some non-linearities in each layer and having maybe some layers instead of.
I mean, it is always better to have linear layers in between than not have them, right? You can have multiple nonlinearities by having more and more layers that include nonlinearities. But if you take out the linear basically layer, the linear transformation in between different nonlinearities, you're just gonna lose some flexibility of your model, right? So worst case scenario, it is gonna learn an identical map from one layer to the next layer, if that's basically what data requires it to do, right? So what you're saying is within that's basically setting, right? You have multiple nonlinear layers, one after each other. And let's say that our model only learns a linear map. And basically it just takes your data and gives the exact basically data to you, right?
Yeah.
I mean, depending on the size of the matrix and everything, but still.
Okay, thanks for the discussion. Yeah.
All right. So we said that we have basically this computational graph, and now we want to use this idea in order to learn to basically demonstrate backpropagation, how it works. So let's assume that we have a feed-forward neural network with fully connected layers. That means that we have basically multiple layers in which we have a linear transformation. I'm not even thinking of basically bias here. So I have a linear transformation. I'm multiplying y with some matrix W, and I'm getting some output, and then I am applying some nonlinear layer over this, and I'm getting the basically activation for that layer. So I can represent that using a computational graph. I can say that I have some input x, which is equal to my y0, right? And then I have matrix multiplication of that with some weight w, and that will give me a new variable z1. Then I apply some nonlinear basically layer on this. So the operation is just applying element-wise nonlinearity on my input z1, and that will give you new variable z, basically y1. And I can continue this for multiple layers, cascade of layers. I take that until I get some prediction. Here I'm showing that y3, and then I have some labels y hat, and I want to compare them using some objective function, some loss function L. Depending on my task, I can have different type of basically equations. So I'm not specifying it what type of operation is this, but it is just a function, some operation based off of my inputs y3 and y hat. So I get our loss function. Now the idea is for backpropagation is that I want to compute derivations of basically all the variables of basically of the loss function with respect to all of our model parameters. For instance, let's look at derivative of L, our loss function, with respect to this variable. So this computational graph can help us to basically write that with more ease. Let me just show it here. So here, okay. So I have this function L, and I want to compute its derivative with respect to W2. So I start with L, and I say that my L is a function of y3, and that's a function of z3, and that's a function of y2, that's a function of z2, and that's a function of w2. So I'm just finding the path that shows how w2 is a parent of L, function L, in the computational graph. Next, I'm going to compute the derivatives in the order using chain rule. I'm going to say that the derivative of our loss function with respect to W2 is equal to derivative of L with respect to Y3 times derivative of Y3 with respect to Z3 times derivative of Z3 with respect to Y2 times derivative of Y2 with respect to Z2, and that times derivative of Z2 with respect to W2. And that's going to give me a relation based upon chain rule that I can with basically compute the derivative of my loss function with every variable that I have here. I just need to see how basically from what path I can get from that variable to my loss function, and I just go backward and I compute basically derivative of loss in each step and multiply those using chain rule, and I will get my basically gradient here, and that gradient is going to be used to update parameters W2. So I'm going to continue and find this for W1, W2, W3, and every basically parameter that the model has, and that's going to help me to update my model parameters.